Hi everyone, let's review the quiz that we have on applications of first order equations, so in physics. And I'm going to do two types of questions. So I promise you the quiz will be out of one of these. So it's either a mixing problem or it is a gravity problem. Okay, so let's look at these problems in detail a little bit. So we have the first question is that I'll read it with you. We have a town. That doesn't matter really. We have a reservoir containing 10,000 of liters of drinking water in which they have mixed 30 grams of chlorine. So chlorine is a substance that is used to purify, to keep the water bacteria free. It kills bacteria. And at these low doses, it's not harmful to people. The town arranges with the water treatment plant to add water to the reservoir because they want to make more, they want to keep using water, right? So they have to get new water, and the rate is at 100 liters per minute. That water is treated also with chlorine, and that the concentration there is 5 milligram per liter. Now, at the other hand, of course, they want to give the water to the townspeople, so what they do is they drain it at a rate of 50 liters per minute, the mixture. And so we're assuming that the whole thing is always constantly mixed. And the question is find the amount CT of chlorine in this tank at any time t. So we were looking for C. And what do we know? We know that the rate at which C changes, I want to write my C a little bit this way. Okay, that's my way of writing a C, to capital C. So we know that that's the rate of change. There are two types of rates. What C changes? Well, there's the rate of the inflow that is adding to it, and then there's the rate of outflow that we're gonna have to subtract for it. Okay? And how are these rates calculated? So a rate that will be, it's the concentration of chlorine times the rate of change of the water. Okay, I hope that formula is clear, right? The water changes because we're putting in water or we're draining water, that depends in either case. And that water has a certain concentration of chlorine, and that's if you multiply the rate at which the water changes times the concentration of the chlorine, then you get the rate at which the chlorine changes. Okay, so let's figure this out in both cases. For the inflow, what is the rate there? Well, the concentration of chlorine. What is the concentration of chlorine in the water that they add? So the inflow is discussed in this part of the question, right? And we see there's 100 liters per minute of water and 5 milligram. Be careful. So what are the units here? We have liters. We have we have grams. You see here we use gram here in this thing, and we also have T is minutes. T is in minutes. Okay, and we assume. Okay, no, let me not say this at the moment. So that T is in minutes. This is grams and liters. Now I say 5 milligram here, so we have to be careful. So a milligram is 1,000 of a gram. Okay, so what does that mean then? The concentration of Clorox. Not Clorox, of chlorine. Clorox would be a bit too, that only silly presidents want you to consume Clorox. Okay, so what is the rate here is 5,000 per liter. So the concentration of Clorox per liter, of course, chlorine per liter, that's the concentration here, times, what's the rate of change? Well, it's the 100 liter per minute here. Okay, times 100. So if you multiply this we see it's a constant rate of 5/10, which is a half. Okay, that's the inflow. Now, what about the outflow? Let's do that in blue. Where is that information? That's the next thing, right? So this is about what they say here, the water that they take out. Now, there we see that it is the water from the tank. And so what we need to know is what's the concentration. What's the concentration of the water of chlorine in the tank? Well, that will be how much chlorine there is in the tank times divided by the how much water there is. This is the concentration of chlorine. What I wrote right down. The amount of chlorine divided by the amount of water. Right. That's what we always how we calculate this 5 So that's the concentration, and now the rate of change that is given that by this number 50. Okay, so times 50. So what is this? Now, C, we're setting up a differential equation for C. So it's okay that we don't know C. We can leave C as it is, but W is something new. So can we figure out W? Yes, that is not hard, because W is the amount of water, but we know exactly what happens. Everything is constant here. There's a constant amount of water added. There was an original amount of water, so we have to also take this now into account. This is the original amount of water, so this is at t equals 0. We had 10,000 liters, so we had 10,000, the original amount. Now, how much liter do we add? That's the green part, tells me 100 liter per minute, so 100 t. But we also subtract, that is the blue part. It says we're subtracting it, we're draining it by 50 by t. So we see that this comes out, let me go back into black here, 10,000 minus 50, plus 50t. So let's write down now what we have here. The outflow is C, which it's okay, we don't know yet, but that's the equation that will tell us what it is. Then we have 10,000 plus 50t times 50. I can actually factor out the 50 here, so let's work it out a little bit. So 50c here, we can factor out the 50 and get 200 plus t here. Oh, that's nice, the 50 is cancelled. And then you get c over 200 plus t. So, conclusion, what's the differential equation here? So this is my capital C, right? The differential equation is the difference of these two rates. The constant influx, 1/2, minus this outflux, which is 200 plus t. Okay, so this is the differential equation that we now have to solve. So step 1 is we look at the complementary, the homogeneous equation. So that would be C prime equals minus C over 200 plus t. We know that we have to separate the variables, so that would be dc, I'm going to already do it that way, over c here, and then what do we get here is minus dt 200 plus t. Great. If I antiderive this, these are clearly ln's, so this is the ln of c equals minus the ln of 200 plus t plus a constant. We need the general solution, so we're looking for the general homogeneous solution, right? So we want to get rid of the ln's by exponentiating, so we get a c at this side. Here we get e to the minus ln 200 plus t times the plus d here. Now let's work that out. We can split this sum as e to the power d, that we will now call c then later on. And what do we do with the minus here? We bring that inside, right? So it's e ln 200 plus t to the power negative 1. Remember, a coefficient in front of an ln becomes exponent inside the ln. Be careful, don't do that wrong here, otherwise you get wrong different things. Yeah, it's very easy. If you make a mistake, and especially early on, the whole thing can be really bad, and then you get stuck. And so if you get equations that are wild and don't look, I'm not saying that there's going to be a fraction there might be a radical in there, but really weird things, you could think, let me start over again. Probably the numbers are getting too ugly here. I'm not guaranteeing that they're not going to be always, they could be a little bit ugly, it's the nature of these problems, but okay. Keep it going on. So this I'm now going to call C, so little c, okay, to make the difference. That's a bit confusing perhaps. Capital C is little c, and then the e and the ln's cancel, so then we have 1 over 200 plus t. I write it already with the negative exponent, means reciprocal, right? So that is my general solution. I can put a little c here if you want, yeah. Perhaps the c is a little bit confusing. Let me put a k here, otherwise you might get a little bit confused, and I might be confused between my c's and my k's. As you by now must have realized, my writing is not the greatest. Okay, so here. Okay. So step 2, we now need, this is the general homogeneous solution. We need a particular solution of the actual equation. This is not a solution of the actual equation. So we know that this will be by the variation of parameters, we call this. Let's give this a name because we're using it so often. That means we're going to take a solution of the homogeneous one by choosing a value for k, here k equals 1, and multiply it with u. So this would be, in this case, be careful, it's not exactly replacing the constant by u. Don't because the constant is often like that, but in linear first order it is always like that, but in more complicated differential equations it's not like that. So follow the instructions clearly, accurately. Okay, but anyway, this is what we have. Perhaps it would have been better to keep writing it this way, because I have to do calculus with this thing, and it's easier to write it as powers. So okay, what we're going to do is now we're going to calculate this derivative and plug this in the differential equation. So u prime 200 plus t to the power minus 1 plus, copy the first and now take the derivative of the second. That's a minus 1 coming out, and then we have 200 plus t to the power negative 2. Okay, and that we're going to plug into this differential equation that we have here. Let me perhaps copy it. So what do we get? U prime 2. Well, now, because we're going to look at an algebraic expression and see where we cancel, it might be better to write the exponents now as as fractions, the negative exponents. So I'm going to do that. So we get u prime over 200 plus t minus, we have a minus u over 200 plus t squared equals a half minus c, no, be careful, c is u over 200 plus t divided by 200 plus t. Don't forget, there's a c here, and c is this expression. Okay. So what we have here, let's see, we know the cancellations must happen, and in fact the terms that contain a u must cancel. Let's look at this term. There's minus u 200 plus t squared in the denominator, but that's the same thing we have here, right? If we combine this with this, we get 200 plus t squared in the denominator, and they are both, so these two cancel, and so we get the, oh, my pencil, okay, sorry. I'm going to try to do this quickly. So u prime is, bring this to the other side, is 200 plus t over 2 with a minus sign. So this is perhaps minus 100 minus t over 2. And so u is equal to minus 100 t minus t squared over 4, right? Divide by 2, but I have already the 2 in the denominator here. Did I bring the 2 in the right side? I hope I did the right thing, right? Yeah, I think I did right. Wait, no, there's no negative sign. Sorry, there's no negative sign, right? The negative signs were gone. So there's a positive sign here. So this is plus and plus. I'm sorry about that. So plus and plus. Okay. That's my u. So I see now that c itself is 100 t plus t squared over 4 divided by, this is u, right? 200 plus t. Okay, and I don't like the 4 in the denominator, so I'm multiplying top and bottom with 4. That is 400 t plus t squared over 800 plus, what is that for a weird thing? I guess because it gets plus 4t. Okay, but that's not necessary. So what is the general solution? So step 3. It's the homogeneous solution, c over 200 plus t plus the particular solution plus 400 t plus t squared over 800 plus 4t. Okay, sorry, give me a sec here. Okay, so now we need to calculate c. What is the at time 0, do we know what happens at time 0? We haven't used that information really. The only one that's the orange here is that it was 30 grams. It's the amount, we just have to put in the amount, 30 here. So if I put in t equals 0, so what we get then, we get 30 is equal to the little c that k, we're calling it k, sorry, little k, 200, plus, and then if I put in 0, I get just 1 over 800 here, right? Okay. So if I put this on common denominator, say 4k plus 1 over 800 is 30. So bring that to the other side, we get 2400, no, 24,000 equals 4k plus 1. So 4k equals 24,000 minus 1. So k is equal to 2,399 over k. Over 4. And so the general solution, so the solution is that constant that I just found, 23,999 over 4, which is about 6,000. I mean, of course, at this level, that little detail doesn't make much of a difference here. So we could put it equal to 6,000, but now, perhaps here, okay, the way I integrated this separately, right? And sometimes it would be better. Remember, you can choose a constant here. So this is the constant, but if you integrate this in this fashion, you get a half 200 plus t squared divided by 2. So it is a bit easier to work with this quantity here. You see it's different, right? This is not the same as this, but it's the same up to a constant. And if you do it this way, you see that the formula becomes a bit nicer. So let me do this here. I'll do it in a different color, but I have to rush a little bit because I'm worried that my pen is going to run out. And we do the second problem in a different video. So red is going to be the same answer, but using this form instead. So C would now be equal to U, which we calculated here as 1/4. If my pen is dying, then this is happening. 1/4 200 plus t squared divided by 200 plus t. Right? And see, this is much easier to see now. This is 1/4 times 200 plus t. That's the particular solution. So I can make this much more compact here. The general solution is k over 200 plus t plus 1/4 200 plus t. Okay, and this is much easier to work with if you want. And of course, the k will now be slightly different because I chose a different particular solution, right? If you take a different particular solution, then all solutions are there, but they're generated by different constants now. So in this case, we would have 30 equals k over 200, but t equal to 0, plus 200 divided by 4 is 50. And so this is much easier to see now what k would be, right? So minus 20 equals k over 200. So we get k is equal to minus 4,000. And so the solution, therefore, is the solution that we look at is minus 4,200 plus t plus the particular solution that we had here, 200 plus t. Now you might not be convinced that it's the same, but this is now the same. Okay, I said this was almost wait, 4,000 minus 20, yeah. Anyways, I'm not going to go check it out, but this is, so ignore the, perhaps, let's not, what I did here first, it's a bit more confusing, perhaps, you don't see really what is happening here, so I'm sorry. Go back to the solution that I did where we integrate this without splitting it. Okay, of course the half comes out, but using the power rule on the whole thing, because then, and if you, this is what we often does in these kind of situations to get the nice constants. That's the only thing we're doing, trying to get a nice form. This is not wrong what I did first, but it is much messier. I hope that is clear. Okay, so I'm going to stop this video, and in the next video I'll do the other problem. All right.